Imagine the universe as a newborn baby. Wouldn't you want to see a picture of it? Well, we have one. It's called the Cosmic Microwave Background, or CMB for short. This isn't your typical photograph. It's a faint glow of light that's been traveling through space for billions of years. The CMB is a relic from a time when the universe was young and hot, a time when atoms were just beginning to form. To understand the CMB, we need to go back to the very beginning. Imagine a universe so hot and dense that atoms couldn't even exist. Electrons, protons, and photons zipped around in a chaotic soup. Light couldn't travel freely in this cosmic fog. It constantly bounced off the free electrons like a flashlight beam in a dense fog. But the universe was expanding and cooling. As it cooled, a dramatic event occurred: recombination. This event changed everything. It's the reason we can see the universe today, and it's the reason we can study the CMB. So buckle up. We're about to embark on a journey through time and space. We'll explore the mysteries of recombination and the CMB. Get ready to unravel the secrets of the early universe. In the early universe, things were extremely chaotic. Imagine a dense, hot fog trillions of times hotter than the surface of the sun. This fog wasn't made of water vapor, though. It was a sea of charged particles, mainly protons and electrons, along with light particles called photons. Photons, the particles of light, were constantly bumping into the charged particles. They couldn't travel far without getting scattered in random directions. This constant scattering made the universe opaque, like trying to see through a thick smoke screen. Imagine trying to look through a crowded room filled with people constantly bumping into each other. You wouldn't be able to see very far. That's what it was like in the early universe. Light couldn't travel freely, making it impossible to see anything. This state of constant scattering and opaqueness lasted for about 380,000 years after the Big Bang. It's a period known as the opaque era, but the universe was cooling as it expanded. And this cooling set the stage for a dramatic change, a pivotal event called recombination. As the universe expanded and cooled, a critical threshold was reached. The temperature dropped enough for protons and electrons to combine. They formed neutral hydrogen atoms in a process aptly named recombination. This wasn't an explosion or a sudden event. Think of it more like a gradual transition, like when the temperature drops and fog slowly dissipates. Before recombination, the universe was like a crowded party with photons constantly bumping into charged particles. But as neutral hydrogen atoms formed, the photons were free to move. The fog cleared, and the universe became transparent. Imagine the party guests suddenly pairing up and sitting down. The room would become less crowded, and you could finally move around freely. That's what happened to the photons. They were finally free to travel across the universe. This moment of first light is what we see today as the cosmic microwave background. This ancient light has been traveling through the universe for billions of years, and it carries a wealth of information about the early universe. The CMB is more than just a faint glow in the sky. It's a treasure trove of information about the early universe. Think of it as a baby picture of the cosmos, a snapshot of what the universe looked like when it was just 380,000 years old. This baby picture is incredibly detailed. It's not a photograph in the traditional sense, but a map of temperature and density fluctuations in the early universe. These fluctuations are tiny, just 1 part in 100,000, but they are incredibly important. Imagine a perfectly smooth pond. Now imagine dropping a pebble into it. The pebble creates ripples that spread outwards, creating a pattern of peaks and troughs. The CMB is like the ripples on the pond. These ripples reflect the tiny density variations in the early universe, which acted as seeds for the formation of galaxies and galaxy clusters. The cosmic microwave background, or CMB, is like a time machine, allowing us to peer back into the distant past. By studying its properties, we can learn about the conditions in the early universe. This includes its temperature, density, and composition. We can determine what the universe was made of back then. And we're not just talking about ordinary matter like protons and neutrons. The CMB provides evidence for dark matter and dark energy, these mysterious substances that make up the vast majority of the universe's mass energy budget. Imagine finding an ancient artifact that reveals secrets about a long-lost civilization. The CMB is like that artifact. It provides us with clues about the fundamental building blocks of the universe and the rules that govern its evolution. The CMB tells a story of a universe that was once incredibly hot and dense. a universe that has been expanding and cooling for billions of years. And it's a story that's still being written. The cosmic microwave background, or CMB, isn't just a uniform glow across the sky. It has subtle temperature variations, hot and cold spots that form a pattern. This pattern, like a fingerprint, is unique to our universe. Think of a fingerprint. No two fingerprints are exactly alike. They are unique identifiers. The pattern of hot and cold spots in the CMB is like a fingerprint for our universe. These temperature fluctuations are incredibly small, just a few millionths of a degree. But they tell us a lot about the early universe and the processes that shaped it. They are the imprints of sound waves that traveled through the early universe. Imagine a drumhead vibrating. The vibrations create a pattern of peaks and troughs on the surface. The temperature fluctuations in the CMB are like those peaks and troughs, frozen in time. Scientists have created detailed maps of the CMB using sophisticated telescopes. These maps reveal the distribution of temperature fluctuations across the sky. They provide us with a wealth of information about the early universe. Imagine having a map of Earth as it was millions of years ago. You could see how the continents were arranged, where the mountains and oceans were located. The CMB maps are like that, but for the entire universe. By studying these maps, we can learn about the geometry of the universe, the amount of dark matter and dark energy it contains, and even the physics that governed the universe in the first fraction of a second after the Big Bang. It's like piecing together a jigsaw puzzle. Each piece or temperature fluctuation provides us with a small piece of information. But when we put all the pieces together, we get a clearer picture of the early universe. The CMB is not a single picture, but a series of snapshots taken at different stages in the universe's evolution. As we develop more advanced telescopes and techniques, we can capture images of the CMB at different frequencies. Imagine having a baby album filled with pictures of a child at different ages. Each picture would show how the child has grown and changed over time. The CMB is like a baby album for the universe. These different pictures allow us to track the evolution of the universe over time. We can see how the temperature fluctuations changed as the universe expanded and cooled. And we can use this information to test our models of cosmology. It's like watching a time-lapse video of the early universe, seeing how it evolved from a hot, dense soup into the structured cosmos we observe today. And with each new observation, we gain a deeper understanding of our cosmic origins. The story of Recombination and the CMB is a testament to the power of human curiosity and ingenuity. By studying these faint echoes from the early universe, we are unraveling some of the biggest mysteries in cosmology. We are like cosmic detectives, piecing together clues from billions of years ago to understand our place in the universe. And the more we learn, the more we realize how much more there is to discover. The universe is full of wonders waiting to be uncovered. And as we continue to explore, we can be sure that the cosmos will continue to surprise and amaze us. The journey of cosmic discovery has just begun.